Right. So good morning, everyone. Thank you very much for joining our guest lectures for today. So with us is Professor Wang from University of Science and Technology of China, from Hefei and Hui, China. So Dr. Wang is an expert in many facet Rasch model, graduated from University of Georgia, US, okay, under supervisor of Professor George Engelhardt. So Prof. Engelhardt already become our guest lectures last year, right?
Ah,
Yes, and we are very glad to have you here and share something about many facet Rasch model. Is a new advanced analysis that involve Retters and Reti, all right? So we will have around 40 minutes for lectures and then follow with discussion and question and answer, right? Is it okay for you? Right, so without further ado, so Prof. Wang, the screen is yours.
okay. So I'm gonna start. Can you hear me? Okay. Okay, great. I'm gonna start sharing my screen of the slides. Can you all see the PowerPoint now? Is it working?
Yes, yes.
Okay, perfect. So you can stop me in the middle if you have any question. And you can also save your questions at last. It's totally up to you. So thanks very much for inviting me. I feel very happy to be here and share some of my thoughts and my research related to the manifested Rasch model. So as Bambang introduced, that I studied with Professor George Engelhardt at University of Georgia before, and I specialized in examining the written-mediated assessments with actually various latent tree models, and manifested Rasch model is one of them that can provide some really useful information with a particular perspective of the rater focus. So I'm gonna introduce the manifested Rasch model today, but with an application or illustrative example on the written-mediated assessment. So the outline for the talk today, I will first share the perspectives on invariant measurement, because we're talking about measurement and we can never get. I can hear my own echo. Let me see. Does it bother you? I hear my own echo here.
Yes, Prof. We hear your echo too.
Do you hear echo too? What's the issue? Should I use the earplug? Would that be better? One second, sorry about that. Technical issue.
Hello? Is it working?
Yeah. Much better.
Much better. You don't hear echo anymore, right? Okay, so I'm gonna first share the perspectives on invariant measurement and then introduce the Rasch measurement models, and then end up with illustrative example in creativity assessment, and also introduce the use with the Facets computer program, if you ever heard of that. That's a specialized computer program for analyzing manifested Rasch model developed by Mike Lineker. Okay, let's get started. So there are various codes that emphasize the importance of invariant measurement. For example, Stevens said that the scientist is usually looking for invariance, whether he knows it or not. And the scientist seeks measures that will stay put while his back is turned. And Rasch mentioned this is the Rasch who developed the Rasch models. So he proposed the concept of objectivity that raises fundamental problems in all sciences. For a statement to be scientific, objectivity is required. And then the Wright once said that science is impossible without an evolving network of stable measures. So we want that when in educational assessment, when we develop some measures, it can be objective, it can be invariant across different conditions and across different time points. So with that in mind, let's look at some examples that are very common in our life, or we can call that as measurement in physical sciences. We use ruler to measure the length, right? We look at the clock to see what time it is, and we also measure our own weight using a body scale. So all of those, we trust them, right? When you look at the clock, for example, when you look at a phone, you wouldn't really worry about the inaccuracy of the time. Maybe if you're using your watch and different people have different watches and the time may have some measurement error, but we still trust it. But in social sciences, we also do measurement, right? We develop different scales for measuring different constructs, different latent variables. For instance, here we have a global scale for measuring food insecurity experience among adults. And this is used across the countries by the Food and Agriculture Organization of the United Nations. And this is a very widely used universal scale that has been applied in practice. However, this scale has been maintained over the years, has been adjusted all the time. So the measurement in social sciences, when we develop the scales, what we want is that we can calibrate the items along the scale. And we can also find, for example, setting the standards for meeting the moderate or severe food insecurity for the persons. So it's a similar idea as building a ruler. And on this ruler, the items are like the anchors. And then the persons, we're trying to measure which level this person is at using this ruler, using the scale we constructed. So we can do a quick comparison between the measurement in physical sciences versus social sciences. So when we measure an object, a physical object, it's much easier in some ways, since it can directly observed. When we measure the table, we see it, it exists. But in social sciences, if we measure the psychological construct of human beings, of ourselves, such as developmental stages of infants, writing proficiency of the students, teaching motivation of the teachers, and the attitudes toward the politics or attitudes toward something can be more difficult since it cannot be directly observed. We cannot really see through people, see how proficient their writing is and how motivated they are in their teaching. It cannot be directly observed. How do we observe? Through the behaviors. So these unobserved or latent variables are also referred to as constructs. So we're building the measures, or this process can also be called as construct building or construct development. So similarly, researchers will develop scales to measure the constructs, and there are two difficulties. The first one is that the different instruments that are designed to measure the same construct may provide different measures for the same person. So you can imagine that you have a survey, and the same person came in and completed the survey, the same questionnaire, and you may get different scores at different time points, or just by repeated measures, you may get different scores. It's not that easy as you measure your own weight twice using the same scale. And the second difficulty is that the same instrument may work in different ways for different persons. So we may have some interactions, some unique interactions between ourselves and the questionnaire or the items on the questionnaire. We may interpret the items differently, and that causes the bias, and that contributes to the measurement error. So we want the invariance in measurement, or we can say we want the objectivity of the measurement. So Rasch first proposed this idea called specific objectivity. And later on, Wright used a different term called objective measurement, which means similar idea, similar concept. And then Professor George Engelhardt developed this kind of extended the idea, extended the concept to a more broader sense using the invariant measurement in his book. But the central idea or the essential concept behind it is actually based on the comparisons. On one hand, the comparison between two stimuli, for instance, two items, should be independent of which particular individuals were instrumental for the comparison, and should also be independent of which stimuli within the considered class were or might also have been compared. In short, we're saying that no matter what items you're taking, what form of the test you're given, the comparison should be objective. And also, no matter your which gender group you're in, which class you're in, which population group you're in, this measurement instrument, those measures should be equally difficult, should be also objective. On the other hand, symmetrically, a comparison between two persons, two individuals, should be independent of which particular stimuli with the class considered or instrumental for the comparison as well. And it also should be independent of which other individuals were also compared on the same or on some other occasion. So we also want the comparison between two individuals to be objective. So those two are the kind of the requirements for us to consider in building the measures. But not all the measurement models can satisfy those two requirements. That's why Rasch proposed this kind of family of Rasch models at the very beginning. In his very original work, very early work in 1961, he wrote the following paragraph. I'm going to read it to you. Lately, the statistical methods of psychometrics have been severely criticized in psychological quarters. Thus, Skinner maintains that if order is to be found in human and animal behavior, then it should be extracted from investigations into individuals, and that psychometric methods are inadequate for such purposes since they deal with groups of individuals. And as regards abnormal psychology Zubin states, resource must be had to individual statistics, treating each patient as a separate universe. Unfortunately, present-day statistical methods are entirely group-centered, so that there is a real need for developing individual-centered statistics. And you can see this, the essential element here are the focus on the investigations into individuals and the development of the individual-centered statistics. So at that time, the group-centered statistics, for example, the statistics developed based on classical test theory are dominating the entire measurement field. And then people or researchers have been have realized that the group-centered statistics cannot really provide the objective measures for the persons, especially it cannot provide the really the individual-centered measures. So that's Rasch's motivation for creating or introducing this new set of the measurement models. So before we look at the model form, let's learn a little more about the idea using this kind of hypothetical example. So suppose now we have 10 persons solving 6 items. So we have 6 columns here representing 6 items. And we have 10 rows here representing the responses by the 10 persons. The plus sign indicates a correct answer, and the O here indicates an incorrect answer. And we can see that some questions they got correctly, and some questions they got it wrong. And first of all, let's order the items according to the difficulty. that is reflected by the number of correct answers to each item. So we see at the bottom, we have the column sums. So for item 4, there are 9 persons got it correct. And for item 3, only two persons got it correct. So we may have a rough idea that item 4 is easier and item 3 is more difficult, or is the most difficult among the set of items. And after that, we can do one more ordering based on the person scores. So we order the persons by their ability, which is reflected by the scores, by the number of items they got it correctly, to solve each single item simply by using their raw scores. So we can see that person 3 and 5, these 2 students got 6 items correct. So got all of the items correct and got a perfect score. And we can see a person 8 didn't get any item correct. And that's another extreme score with a total score of 0. And the other possible scores in the middle ranges from 1 to 5. At this point, you may see a pattern in the middle, right? Which is a triangular. If we draw a triangle here, you may see that along the edges. So this is kind of the idea for building the Rasch scale. So we can rank all of the persons, we can also rank all of the items, and eventually you can see another requirement here is that we expect a person got an easier item correct before this person got a harder item correct. So if you see a plus sign here, we may call that as an error, and technically it's called a Gatman error because this follows a Gatman pattern. So this is really an ideal situation that we have all the plus signs in the upper left corner and all the incorrect responses on the right lower corner here. But if we have another 0 or another O here, so that means this person 1 should get item 2 correct. However, for some reason, this person got it wrong. So that's also an unexpected response. It may be an issue related to the item. It may also be an issue related to this person. So we can further analyze the fit indices, the fit between the data and model to investigate the reasons behind it. So that is called a Gatman scale, which is designed to create a single continuum for the joint ordering of persons and items. And the person should answer an easier item correctly before getting a harder one correct. And Gatman scaling sets the foundation for item analysis. So as you see, if there's any misalignment or there's any unexpected response, then we can further look into the items. That is closely related to the probabilistic scaling using the Rasch measurement theory. So the underlying assumption of the Rasch scaling is actually the expected Gatman scale or expected Gatman pattern. So Rasch scaling is probabilistic so that we want to reproduce a Gatman response pattern based on the Rasch measures conditional on sum scores. And the reproduced Rasch-based probabilities can be used to obtain the residuals and further calculate the fit indices for the Rasch models. And we will look at the calculation of residuals and also the fit indices in a moment. So in educational assessments, the meanings and interpretations of scores are essential. And we want to and that determines the impact of our research in the social, behavioral, and health sciences. And we want to frame the substantive conclusions and inferences ultimately, delineate and limit the policies and practices derived from our research work in the social, behavioral, and health sciences. That says our inferences are very important. It's kind of high stake. So as Messick said, the term score is used generically in its broadest sense to mean any coding or summarization of observed consistencies or performance regularities on a test, questionnaire, observation procedure, or other assessment devices such as work samples, portfolios, and realistic problem simulations. Okay, now we can take a look at the dichotomous Rasch model. And here's a modern form, a form that's been used most widely. In this form, this is the natural log, and then we take the odds ratio using the natural log. The odds ratio is the ratio of the correct answering a problem over the problem of incorrect answering problem. And that has been expressed, the log ratio is expressed as a linear combination of the person parameter and the item parameter. For the person parameter, that reflects the ability level or the degree of this person's ability. And for the item parameter, that denotes the difficulty level. And you see that we use a minus sign for the difficulty parameter, which means the higher the measure, then this item has is more difficult. You can also switch this sign to be a plus, even though it's not, usually we use the minus sign. If you switch this to be a plus sign, then delta refers to the easiness. So the higher measure of this parameter, it indicates easier, indicates more easy of this item. And we can also get an alternative form in its probabilistic form using the in its probability function. So you can see that instead of using 0 or 1, we use x to denote, and then in the numerator we have the x here. When x equals to 1, then we have exponential of this difference between the degrees ability and the degree of item difficulty. And when x equals to 0, not solving the problem or incorrect answer, then in the numerator we simply have 1. And in the denominator, it's a sum of these two numerators. So when we add up the p and I1 and p and I0, we always get the sum of 1. And here's an interesting observation. When theta n equals to delta I, what does that mean? That means the item difficulty is exactly corresponds to the person ability. So it has equivalent degree of item difficulty and person ability. At that moment, in that case, then the probability of solving that item is 50%. So they're 50% of getting it right and 50% of chance of getting it wrong. And if the item is more difficult, which means delta I is larger, then this term would be smaller. Then the probability of getting an item correct would be lower than 50%, would be smaller than 1/2. And if theta n is greater than delta I, which means this person is more able compared to the difficulty of this item, then the probability of getting this item correct or solving this problem would be greater than 50%. I think that makes perfect sense in practice. And now let's look at the response functions. Based on the interpretation explanation of the equation of the Rasch model, we can get this idea that for a single person, each line represents a single person, and here we have 4 persons. With the increasing of the item difficulty, the probability of getting the item correct would be decreasing, monotonically decreasing. So when the item gets more difficult, then the probability of answering it correctly would keep going down. And we can also see that person D is more able with the highest ability estimate, and then person A has the lowest. And then the probability of getting the items correct will always be higher for person D than for person A. So this is also non-crossing response functions, which maintains the invariant measurement property in the Rasch model. And this is actually a very unique and very nice feature of the Rasch measurement theory. And similarly, for item response function, those 3 curves represent 3 items, item 1, 2, 3. And then with the increasing of the person ability, so when the person gets more able, then the probability of answering an item correct would also be monotonically increasing. And we can also see that item 1 is the easiest item among those 3 items, and item 3 is the hardest, is the most difficult. And then no matter for which person, regardless of the individuals, then the probability of answering item 1 correct will always be higher than the item 3. So this is also another set of non-crossing item response functions, which maintains the invariant or objective comparison that as Rasch, Wright, George Engelhardt proposed and promoted over the years. Okay, and now let's look at extensions to a family of Rasch models. As we get familiar to the expression of dichotomous Rasch model, then we know that we have 2 parameters, theta n and delta I. Theta n is person ability, and delta I refers to the item difficulty. And then we can extend the dichotomous model to the polytomous models, including the most commonly used ones include the partial credit model and rating scale model. And you can see the only difference is that in the partial credit model, we have a delta I k. We add one more subscript here to denote different categories within each item. And for the rating scale model, it can be viewed as a reduced version of the partial credit model by having a common threshold structure across the items. So with the partial credit model, we allow each item to have its own unique structure or each unique estimates of the categories. With the rating scale model, for instance, with the Likert response, the Likert type responses, sometimes we want the categories to be equally to be spaced the same across, to be distributed equally across different items. Then we can estimate, we can fit the rating scale model with a common threshold structure on the top here. And then let's look at the many-facet Rasch model that extend the number of parameters to extend only 2 parameters to a set of to several parameters. So at the very beginning, the idea is that we want to consider the assessments that involve reader scoring, which we call written-mediated assessment, but also like some personality test. We may have an observer or some other kind of the third person that comes in and provide their judgment. So that was the original motivation. Mike Lineker developed the many-facet Rasch model by including a parameter lambda for reader, and he called it as scoring severity of reader M. But later on, it can people actually also use a many-facet Rasch model for different situations, for different cases. It can include reader or some other facet when the data is cross-classified. So similarly, for the Rasch, for the many-facet partial credit model, we have delta IK here, and for the many-facet rating scale model, we have 2 terms, delta I and tau k. The only difference, if you compare to the this kind of 2-facet model, 2-facet partial credit rating scale models, we just have one more parameter being added. And actually, other researchers have developed the kind of extended many-facet Rasch model by having more than 3 facets, kind of 4 or 5 facets, by involving some other parts that be involved in the experiment. Okay, and then let's look at the use of Rasch model. Actually, essentially, we're trying to construct a right map. People may also call that as a variable map. The idea is very simple. We have the data, item as experiments, and then we feed the Rasch model. The data and Rasch model, the fit between these two can be an iterative process. We may go back and forth. And based on Rasch model, we get the estimates of the model parameters. And based on the model estimates, we can build the single continuum which maps the items and persons along the scale. And this is so the red map can be viewed as a empirical display of the latent scale or the single or the latent continuum. So the red map it's very nice and very useful visual display. If you use Rasch model, if you apply the Rasch model in your own research, usually we include or report a red map as a result in our paper. And now let's talk about the residuals. Since when we feed the model, we get our expected scores, right? Based on the theta and delta I, based on those estimates, we can reproduce the probabilities. And those probabilities are our expected scores or expected responses. And we have our original responses, the observed responses. For instance, if we have dichotomous data, then the observations are all 0 or 1s. And when we feed the Rasch model, we get our probabilities getting the items correct. So with the expectations, we are trying to reproduce the Gatman pattern. If you remember earlier with based on the hypothetical example, we're trying to reproduce that data matrix with the probabilities. And then we compare our observations and the expected probabilities. The difference between observed and expected is the residual. So we can calculate the residuals using our observed scores minus the computed probabilities based on the Rasch model. And then based on residuals, we can get a set of commonly used fit indices. This is a visual display of how we can obtain the residual matrix. This is your data matrix, the observations. You have 0 and 1s here and there, and persons by the items, rows by the columns, and minus the reproduced expectations, the probabilities based on the model parameters, the model estimates. And then the difference between these two gives us the residual matrix, persons by the items. And based on the residual matrix, we can also, based on the expectations, the expected probabilities, we can get our information matrix. You can see it's simply the P times 1 minus P. It's very simple with the Rasch model. We can get our information matrix. We call that as Q. And later we're going to use Q for calculating the commonly used mean square outfit and in-fit statistics. You can see that we actually create another matrix called outfit square residuals. In this matrix, we're using the square of the residuals, the residual matrix on the previous slide, and divided by the information matrix. We also showed the calculation of information matrix, and here are the equations just for reference. And then we get outfit square residuals, and you can see that when we calculate the person outfit, we simply use the column average, and the row average gives us the item outfit. So that's, if you go through this logic, you will realize it's a very simple idea to obtain the fit indices by the manipulation of the residuals. So that's why when we have an unexpected response or an outlier, then outfit would be super large because it's based on the residual. And when the residual is very large, then the outfit would be large too. For the in-fit statistic is simply the square of the residuals, and then we're gonna weight it by the sum of the information matrix. That's how we calculate the in-fit for the item and person. And similarly, we're getting the column sum for the person fit in the numerator and row sum for the item fit in the numerator. And then let's look at interpretation of fit indices. You do not really need to remember all the equations for calculating them. The equations or the figures here just help you to understand what's behind the indices. I think what we use more what we care more as educational researchers is interpretation and how we can use the actual numbers to identify the problematic items or persons. So the expected value for the in-fit and out-fit mean square statistics is 1. So if the values are very close to 1, that indicates good fit, good item fit, or good person fit. And if you have reader in it, then that's good reader fit. Otherwise, if it's not close to 1, far away from 1, then they are considered as misfit and need to be further investigated. And I know that this statement is a little bit kind of blur, because what do you mean by not close to 1? So researchers actually give different criteria. For instance, this is provided by McLinaker in one of his research and has been promoted by other researchers in their recent books on Rasch measurement models, which is the categorization of the mean square error or the mean square residual in the office statistics into 4 categories. So if it's between 0.5 and 1.5, that is viewed as close to 1. And the items are good fit, productive for the measurement. And you can give a fit category of A. If the mean square residual is lower than lower than 0.5, so it's kind of going far away to the left side, then that's less productive for measurement, but now distorting of measures. So you will we can assign the fit category of B. And if you remember the equation, actually the mean square residual will never go below 0. So this is actually between 0 and 0.5. So if just slightly lower than 0.5, then that's okay. It's not distorting measures, not the end of the world. And then if it's between 1.5 and 2.0, it's similarly not distorting of the measures, but it may be unproductive for the measurement. So it may raise your caution. If you're looking at a high-stake assessment, high-stake educational assessment, then the items with the fit indices between 1.5 and 2 may cause your attention. And for those items or persons with the fit indices above 2, definitely you need to do something with them. Either go back to revise or look at the content and see if it's really not a good item. You may also even consider removing. So they can be distorting of the measures, which means they may create biases for the location estimates of other items and persons. So this category, the category D, really needs your attention, really needs to cause our caution. Along with the reliability, along with the fit indices, usually we use the fit indices to examine how to provide the validity evidence, since it tells us how good fit or how well that data fit the model. With the reliability of separation index, it gives us an idea about how reliable the measures can be. It is the ratio of true score variance to observed variance based on the latent measures. The true score variance versus the observed variance is the definition of reliability. But in the Rasch model, when we call that as reliability of separation index, the calculation is based on the latent measures instead of the raw scores. So the reliability equation is the same, but the standard deviation here is the standard deviation of the Rasch measures, which are the latent measures. And the MSE, the mean square error, is average of the square standard errors also of the Rasch measures. And that's why this reliability of separation index can reflect how well the items or the persons separate or distribute along the scale. The interpretation is the same as other reliability indices. When it close to 1, it indicates better representation. The Rasch measures indicates higher reliability, and it ranges from 0 to 1. And another related concept, or when we talk about the psychometric foundational areas for examining the measures, we cannot really get across, we'll always get across the fairness. So based on the 2014 test standards, right now they are working on a newer edition of the test standards, but 2014 is still the most recent, most updated, the published one. So in that version, 2014 test standards developed by APA, AR, and CME, they put fairness as a separate chapter. fairness actually is closely related to validity. It's the idea that whether it can provide the fair scores or valid scores across different subpopulation groups, because it's very important for the educational assessments. So the test standards set it as a separate chapter alongside with the fairness, the reliability and validity. And Rasch model actually provides a simple and direct approach to examine the measurement invariance between the subpopulation groups. And differential item functioning is used, this analysis is used to detect the statistical bias and also the inaccurate measures. If we really detect the diff of an item, it has threats to validity because it's not measuring the construct it's supposed to measure. And also has threats to generalizability because it cannot be generalized to a different subpopulation group. It may only be valid within one particular group, but be biased to another group. Then it has threats to the generalizability. And of course, the fairness as well, unfair decision, especially for high stake assessment, if it's biased against female or is biased against a minority group, then that leads to really severe consequences for high stake assessments. And also, it may raise ethical issues when the items be biased. Statistically, we can detect this statistical bias using differential item functioning. The central idea is that if it's more difficult for a certain subgroup among those persons who have same ability level, then that's bias. And calibration is usually required because we have to first put all the groups onto a common scale so that we can really say they're at the same level of the ability. And then we can compare how the items perform within each group. So establishing this common scale is very essential. It's very important as the first step of the diff analysis. And in the Facets computer program that I will introduce a bit later, which is a specialized program for analyzing the Rasch model, and particularly for many-facet Rasch model, it uses a two-stage process for examining the diff. And step one is to calibrate all the facets onto the same scale, which is the establish this common scale. And the step two is to include the interaction between the item and the particular group, for instance, gender or the student classes, or the schools, or some other group variables, demographic variables. So we estimate the size of the interaction or the diff effect by adding this interaction term. Okay, so that's kind of the some technical aspects of the Rasch measurement models, and also the perspectives on or the importance of invariant measurement. And now let's look at the most widely used applications of many-facet Rasch model in the written-mediated assessments. Written-mediated assessments are actually widely used in a variety of contexts, and they can be broadly defined as any assessment system that requires human scoring. And most performance assessments involve rater scoring and provide opportunity to measure more complex aspects of student learning, as Susan Lane once mentioned that performance assessments can better reflect students' competencies in applying knowledge and skills to solve educational and meaningful tasks. For instance, writing assessment or language testing, except for the multiple choice items when the students are required to construct some responses, that may require human scoring. And we can also broadly define all of those types of assessments as written mediated. So today I'm gonna talk about an illustrative example based on a subjective creativity assessment. In this data set, we have 48 sixth graders, and they are asked to solve 2 science tasks of creativity assessment. And for those 40 students, half of them were in a gifted class, and the other half were from a regular class. And we also had 45 readers separated into 3 groups, 15 in each group, including educational researchers, elementary school teachers, and undergraduate students who are majoring in elementary education. So we have 3 groups of teachers, 3 groups of readers who have different level expertise. So this actual study originally we're trying to examine reader effect, but we can use this as an example to see how we can conduct many-facet Rasch model analysis. And let me show you briefly the science tasks we used in this example. So task 1 is about how you can survive, how you can find the drinkable water on an unknown ocean island. And there are some descriptions of the objects in the surroundings. And in this situation, the students are asked to use their knowledge and generate the ideas as creative as possible. So this is like a typical scenario-based or context-based problem-solving creativity assessment in science field. And the second task is similar, but it's more about the geography. So the students were asked to imagine if our Earth if there's something happened to our Earth and tipping the Earth's degree more than its current 22-degree tilt, what's going to happen to our climate, to the climate of North America, and how will people adjust in order to survive, and also ask the students to use their knowledge about season and climate and generate ideas as creative as possible. So here, these are the kind of the tasks the students were asked to solve, and they gave their responses, and the readers came in. Those 3 groups of readers came in and score on the student responses using a scale from 1 to 5, representing different levels of kind of the creativity. So 5 being the most creative and 1 being the least creative. So the readers provided their responses using the Likert scale. And then we use the many-facet Rasch model to analyze the data. And you can see this model contains many parameters. And we can do that actually with the Facets computer program is now constrained to only 3 parameters. But we still separate them into 3 groups. So theta n denotes student creativity. And CG is actually closely related to the student. It's a grouping variable for the student. It's student class. So we only have 2 values, class 1, the gifted, class 2, non-gifted. And lambda and R are the reader-related parameters. Lambda I is individual readers' score and severity, and R is the reader group. And we have 3 groups here. And then delta J denotes task difficulty with its the category, the difficulty category. And in this example, we actually used the many-facet rating scale model. So we assume that all the raters use the categories the same, using the rating scale the same. However, our recent research, we're working on another paper, and we're about to submit as well. So in that paper, we applied a many-facet partial credit model. We actually found that the raters use the rating categories really differently, very differently, even in the opposite way. So we're going to update our understanding of the reader behaviors in creativity scoring with a kind of partial credit model. But in this illustration, we used the rating scale model. So before we get into the analysis, let me briefly introduce the Facets computer program. Actually, the most current version is now this one already is 2024. Mac Lineker has been really diligent in updating the versions. And I really recommend buying the full version. It comes with the site licenses for permanent use, and also he sends you the updates for all the kind of the bugs, fix and other things. And you can also email the developer to ask questions. But if you just want to try, for instance, you have a small data set, you can try the mini facets that contains all the features except the limitation to the number of responses, 2,000 data points. And here, just an example of the citation for citing the for if you're using that in your academic writing, you can cite the program using status computer program using this way. You can also find the most updated citation on their website. If you search one steps or facets with Rasch, then it will pop up on Google. So the only difference, if you use a different version, then you need to change the year and the version number here. All the rest remains the same. So with this example, we need to so with the facets, you need to write the input and output file, and this is the input file for the for our illustrative example here, with title, range, facets, all the keywords on the left. And after the semicolon, you can add all the comments you want. That's for own reference. And I listed the key comments here on the title. And you can give a name to our data analysis so that you can remember what it is later on. And facets is a very important comment. You need to really count how many facets you have. And in this example, we have 5. So facets correspond to the number of parameters. We have 5 parameters here: student, student class, reader group, and the task difficulty. And G-stats, you can just let it on to be yes. It just gives you more statistics, produce a point by zero correlation. And the model statement is model comment is another very important comment that specifies which particular Rasch model you want to fit. If you use D, that refers to dichotomous. If you use R, that refers to rating scale, and the number followed, the letter R indicates how many categories you have. So in this example, we use the rating scale model with 5 categories, 1 to 5. Another important element in the model statement is this question mark, this cosine, this question sign. So this question mark represents the facet that we want to estimate. So in this case, we want to estimate all 5 facets. So you see the question mark, comma, separated by the comma. And if you want to, for instance, you wrote the input file like this, but you only want to estimate student, reader, and task in this particular analysis, then you can leave the second question mark to be just a space. You can, or just delete. You can just delete this question mark. And for the group, the 4th question mark, you can also delete and leave the comma being separated. And that means the question mark, the place that you leave as blank, means I do not want to estimate that facet. So only the place you put a question mark, the program will estimate that facet. And the labels just give you give yourself an easier time to figure out what they are in the red map in the output file later on. So it's recommended to have the labels here. And then the rest of them is just the data responses. It can be quite long if you have a lot of data responses. And here, the one thing to note is that the data responses should be separated by the comma as well. And they correspond to your labels here. So the first column is the student ID, and the second is the class label, and then the reader ID, and which group this reader is in, and which task it scores, and this is the actual rating it gives to the student 1. All right, and this is the Facets interface, and you can see the different the click buttons in the menu bar. So usually we click on files, and then under files there is a function called specify file name with a question mark. After click on that, it has a pop-up window, and you just choose the input file on your local drive and then click open, and that will generate the output file automatically and saved in the same folder where your input file is. Very easy. One tip is that input and output files are both the text document. So and also the fastest computer program can only be run with the Windows program. So it's easier that you work with on a Windows computer. And it's easier to use Excel to prepare your data and also organize the output tables. Because sometimes in the text document, it's not that easy to do the copy paste, and also change the like, especially you manipulate the columns. So it's easier that you use Excel to prepare your data and then paste that into the text file. And also after you got the output tables, and paste into Excel for the future organization. Okay, so among all the output tables, what are we looking for? The first one is are the descriptive statistics. We may report a range, mean, standard deviation for the measures for the students' return tasks here. You can see we report the location measures, in fit, mean square, outfit, mean square, those fit indices, and the separation, reliability separation indices. We can see that they're except for the tasks, the students and readers are pretty high, because the tasks will only have 2 and they're kind of equally difficult. So that's why it's not very high. And we can also conduct an analysis called fixed chi-square tests. That test a hypothesis that can the items or the persons or the readers be thought of as, for instance, the items be thought of as equally difficult. And for the students, the hypothesis is, can the students be thought of as equally creative? And for the readers, is, can all the readers be thought of as equally severe? So we can conduct a test using the chi-square, fixed chi-square. It also has a random chi-square. It's totally different. It's a totally different thing. So make sure you look at the fixed chi-square test if you want to see how well they distribute along the scale. But the result usually matches very well with the reliability separation index. So for the student readers here, this test are definitely going to be significant, but for the task with 0.49, this test will not be significant. And another very important output we should be looking at is the right map. So I'm going to spend a few more seconds on the right map to explain what they are. So the measures, the first column shows the measures, the logits, right? Ranging from -2 to 2. And then we have separate columns for the students, class, readers, and groups. You can see for the student class, we have a plus sign as the directionality, which means the higher score or the higher location indicates more creative. So it's in the same direction with the plus sign. Higher means more. But for the reader and reader group, that's more severe, which means the lower score it gives, it has higher location measure. So for the reader and reader group, it's higher location measure means more severe. And then for the task, it's also negative, which also means a harder item would have a higher location measure. But in this case, we can see 2 items are quite equally difficult, and 3 reader groups are also equally severe. And the last column here shows the category, the distribution of the 5 rating categories from 1 to 5, and they're kind of nicely distributed. So this is how we rate a right map. This is generated by the Facets program. However, I did the labeling by myself. So I added those kind of more or less, more creative, less creative, those labels to help the readers, help the audience to understand better. And the students here, you can see a relatively nice distribution with a kind of not normal distribution with more in the middle. And readers as well, we see a little more here, but they are kind of nicely distributed. With 2 classes, we can see class 2 has higher score than class 1. Some of the results some of the questions, research questions we answer in that study, just give you an idea of what tests or what hypothesis we can test with the many-facet Rasch model. For instance, we asked, do students in gifted and non-gifted classes perform equally well on science tasks? We know that class 2 did better than class 1. In the Facets program, it gives you this chi-square test for these 2 classes, and a significant results showing that the gifted class actually have lower, actually performed worse than the regular class. And the other question we asked is that do 3 groups of readers vary in their severity toward the scoring of the student creativity performance? And we see that the 3 reader groups kind of have similar location measures. So the chi-square test was not significant, and 3 groups of readers had comparable scoring decisions in judging student performances. And this was actually a really important finding in our study, which means that the expertise or their kind of background did not matter that much in scoring creativity. So those two are kind of some interesting findings based on this many-facet Rasch analysis for that particular study we have done. And on the fairness evidence, we also examined do science tests show the diff between the gifted and non-gifted classes. And this is the original, the raw table, the original table that Facets program provided. You can see it gives us the measure for class 1, which is negative 0.09, and also a measure for test 2, 0.15, and it gives you the also gives us the t-test with the probability with the p-value. So you can see that both tests actually showed differential item functioning, but task 1 appeared to be more difficult for the regular class, but task 2 was shown to be more difficult for the gifted class. Both are significant. So we can also obtain the fairness evidence. This table gives us the validity evidence and reliability evidence, fit indices, and the reliability separation index. And we get a visual display of the underlying scale using with the right map. And then we can also test our research questions with the chi-square statistics and the fairness evidence as well, the differential item functioning with the many-facet Rasch model. Okay, so here's a very quick summary of the steps that we can follow when we conduct a many-facet Rasch analysis. Step 1, to specify our model. So count how many facets you have, how many parameters you want to estimate, and then write down your equation for the many-facet Rasch model. And then choose a program. I introduced the facets today, but there are other programs. For example, some R packages we can use for estimating the many-facet Rasch model. But still, I think Facets is a very user-friendly program. And the next step is to obtain the location measures, which are the parameter estimates, and then we can create red map at this stage as well. And then we also need to evaluate the quality of the measures using the fit indices, the mean square statistics, reliability separation, and also the fairness issues. So step 4, including 3 sub-steps, reliability, validity, and fairness. And this step 4 may provide remedies to improve the scale. So when we go back to step 3, and this may be an iterative process as well. So step 3 and step 4, you go back and forth eventually until we're satisfied with our measures. And then we go to the step 5, we use the measures for making the inferences or for setting the standards, or we make our admission decisions, for instance. Okay, that's all. Thank you. I see some questions here. So Bemong, how should we do this?
Yeah, I think the first one, can you just stop share screen first?
Oh, stop sharing. Okay.
Yeah. Right. Thank you very much for Wang. So I think all of us got what we call as very wonderful explanation, showing that you are a truly expert. So you explain from theoretical part, technicality, and then interpretation. And then there are some question I think already mentioned here. Pak Suharto, you want to ask directly to Prof. Wang? No, okay. So okay. Okay, go ahead.
Sorry, Prof. Bambang, I'm in the middle of meeting. Okay.
Oh, so-
Okay. Okay. Thank you, Prof. Wang. Your presentation is so wonderful and so interesting to follow. First, The first one is, can we get the PPT presentation, because we want to learn more about the money facet. And the second is, it is possible to combine two type of rating. For example, I want to rating my student performance using money facet trust measurement, and then I use yes, no, or dichotomy rating, something like yes, no, 1 and 0, and the other I do same rating in the same condition with the rating scale for the same measurement. It's possible to do it in facet in the first. And the last is, you show a lot of the analysis that we quite difficult to follow actually, especially if the beginner comes here. It's possible to get what the instrument that you use there and the data sample that you use in presentation, so we can something like rerun the analysis by ourselves. Okay, thank you.
All right, thank you. So for your first question, it's related to the analysis of mixed types of questions, or I think with that called mixed type or mixed form of the questions. So you have
Yes,
multiple, for instance, you have multiple choice. For the multiple choice questions, sometimes we just score as yes or no, correct or incorrect. But we may also have the construct response items that may have partial credits, like 1, 2, 3. So in that case, you can certainly use the Rasch model. You can use the partial credit model because it provides it fits or it estimates a different rating scale or different category structure for each item. So the category estimates for the dichotomous ratings do not affect your category estimates for the rating scale for the ones with more categories. So you can try the partial credit model. I think we may have presented a paper at proms once. I collaborated with one of my colleagues before. He actually used a partial credit model to analyze that type of data. But I don't remember. I think maybe he just published in the measurement of the measurement journal, interdisciplinary research and perspectives. So if you look it up, I think you can find similar research that people have been thinking about this problem with kind of mixed types of ratings and how you can accommodate them using one model. I think partial credit model can be used in this case.
Okay, thank you.
And second, the second question, I cannot really share the creativity data, but I can share another data set, a writing data, because this creativity data is not mine. It's
Okay.
my collaborator collected, so I cannot really share on my behalf. But I can share writing data if that helps.
Oh yeah, thank you.
What
Thank you so much.
helps may be a Facets input file, right? So
Yeah,
if
sure.
I share a Facets input file, you can just revise that input file by yourself for your own purpose.
Yep.
Yeah, that's
So-
wonderful. Okay, usual
Mhm.
source code is important. That's the real secret.
So 1 second, let me get one. And also, okay, I'm gonna share this one. The writing data mentioned in Professor George Inglehart's book, in his Invariant Measurement book, chapter 10. So you can find a very detailed description of this data results in that chapter as well. Yeah, we usually use this data set for our workshop at proms. I think this is the one, data 2. Oh, that's the output. So this is the input. Okay. So the chapter 10 is let me see. Yeah, that's the one. Yes.
Okay, thank you, Professor. Yeah.
You're welcome.
All right. So, is there any other questions? So, I'd like to ask. Okay, Santi, go ahead.
Thank you so much, Professor. Am I audible?
Yes, I can hear you.
Okay, thank you so much, especially for introducing us to the application to do the Rasch analysis. Actually, in our assessment class, we also using the application. We use WinStep. However, your application seems good and we will try maybe. Okay, my question is, oh, so sorry. I'm Santi from master degree student. And then my question is, did you face like any struggle to promote or introduce the Rasch model into the world or academic world? Because as Prof. Bambang, our lecturer said that in Indonesia, mostly the researcher utilizing the CTT, classical text theory. Meanwhile, for those who apply for Rasch, they assume that it is so complicated and they are not familiar with it and they are prefer to use CTT, classical text theory. Did you face like any debate on it with the other researcher or something like that? I'm really curious about that. Thank you so much, Professor.
I think that's a really great question. And I actually think in different countries, we face different challenges. So when I was in the United States, when I was working there, the testing industry mainly used the Rasch model for developing the tests. The familiar ones you may know include the SAT, GRE, and all of those important high-stake tests. They are being developed based on the Rasch models. So actually, the people in our field, especially in measurement field, they can get a job easily. So in America, they understand the Rasch model, the value of the Rasch models, and that's also an issue moving forward. That some tests they start to use other item response theory models, for example, 3PL, three parameter hierarchy models. So they recognize the testing industry in North America. They value the individual center statistics. They value the models that can measure the individual persons, that can conduct item analysis. They value the latent measures. However, they also being they kind of also comparing different models, not only using the Rasch model on one hand. So that's the case in the United States. So in China, it's a little bit different. The researchers here, and also I think sometimes it may be related to the government or the researchers who are at the government, which models they value more or they think they are more important. So in China, they actually the cognitive diagnostic models. I don't know if you have ever heard of that, called CDM, cognitive diagnostic models, which is also a type of measurement model, have been valued a lot in mainland China. So in that kind of model actually works really good for the formative assessments that can provide the diagnosis for the students. It can identify which kind of the knowledge side they didn't master and give a really straightforward report. However, in the high-stake assessment, it's not, especially for summative assessment, it may not be the best model. But Rasch model is not that popular either here, although we know many researchers, we know that it's important, but it's not been valued that much in the practice, in the application, in the practices. But in Hong Kong, I know that for the College of the Mission Test in Hong Kong, they use the Rasch model for the development and also evaluation. So I think it varies across different regions, and I can understand maybe in Indonesia, the CTD in some sense is very straightforward, right? If you get 10 items correct, then that's your score. But for the latent trained models, there's a conversion. So you need to explain to the teachers, explain especially to the parents, why my kid got this rank or got this percentile. Especially when these two kids got exact same number of items correct, but one kid got more difficult items correct, and the other kid got easier ones correct, and then their percentiles being different, right? So you have to explain all of those to the to the stakeholders. So I can see their pushbacks for different reasons on the Rasch models across different areas. And it's understandable, but we're also working and really hard to promote also like people to realize it has its own value. Although we're not saying this is the only model we should use, but it has its own value, especially when we develop and evaluate the instrument. It has a really good property. Does that help?
Thank you so much, Professor.
No problem.
Assessment is not only about technical things doing the analysis, right? So sometimes social aspect is also important. And then
Exactly.
compete with the other measurement model expert who are usually already professors. So you have to find a good strategy how to the two students ask question. Okay, Karamo, go ahead.
Okay. Thank you so much, Pak Bambang. Thank you so much, Prof, for that detailed presentation, even though very critical to understand, because you know anything that deals with mathematical formulas and sometimes it could be tricky sometimes. Okay, I think as a beginner, I'm inspired by Dr. Bambang, and I want to personally try to use Rasch model to at least measure validity and reliability of some of the items I used with my students back at home at the Gambia College. Sorry, let me say I'm Karamo Sise from the Gambia, West Africa. So I want to use these test items to measure the validity and reliability. Basically, from your explanation, is try to, I believe, the partial credit model would do, but I would want you to at least delve at least more into partial credit model for one to venture into that kind of research in order to measure the validity and reliability of the items, to give suggestion or provide whether these items are really valid or the validity and reliability are very good and is indeed worth using testing the students. That's my question.
I'm sorry, I didn't get the question. Can you do you mind?
Okay, speak slowly, Karamu.
Sorry, it's not funny.
So, Prof. Wang, in our class, we have so many accents. So sometimes all
it's
of us
not,
also
it's
have
not
to
the
speak
accent.
slowly.
No, it's not the accent. It just I followed and then I lost. So if you don't mind, can you explain it more?
Yes. I said like I want to use I want to measure the reliability and the
Okay.
validity of the test items.
Okay.
Specifically, is an online assessment. It's an online
Yes.
assessment system.
Uh-huh.
Okay. I already have this course of the students and also the items. Then I want to, from your explanation, is kind of I want to use the partial credit model.
Okay.
Okay. To at least assess this thing. The items there are 45 items and is like multiple choice.
Okay, 45 items and they're all multiple choice.
Multiple choice
Okay.
like A, B, C, and D.
Yeah. Mm-hmm.
Among them, only one is correct.
Okay.
Good. So I want to use Rasch model to measure the validity and the reliability.
To get the reliability and validity evidence, yes, of the scores.
Yes. So I want you to delve at least deeper into partial credit model because I'm a beginner.
Oh, so you're asking which model you should use, right?
Yes.
If you only have multiple choice questions and when you score the items, you have only 0 and 1, then you can just use dichotomous Rasch model. right?
Okay.
So you have only one correct option, right? So the students who select the correct options will get a score of 1, and all the distractors will just be 0. So you have dichotomous reading, dichotomous scores. You can use the most basic, the dichotomous Rasch model for analyzing this set of data.
Okay, and when you have, because sorry, I have also another extra 5 questions that are open-ended, that are open questions. They are theory
Open,
questions.
okay.
Yeah, they are theory questions that need to be answered by writing, giving the opinions of students. So altogether is 50 questions, 45 multiple choice questions, and then 5 open-ended questions.
Okay, so there are 2, this is similar to the first question, I think. So on one hand, you can use the partial credit model, right? If the open-ended questions, you have more than 2 categories. But your open-ended questions, you can also score with 0 and 1, right? But if you determine to use partial credits, for instance, you give 1, 2, 3, right? The full score will be 3, partial score will be 2, and then 0 and 1. For instance, that's your scoring issue. And then you can use partial credit model and combine all the items together to run the analysis. And then on the other hand, you can also try analyzing those items separately. So you can do the multiple choice questions first in one analysis, and then run the open-ended questions in the separate analysis. So I think the selection or the choice is based on what's your purpose. So what's your purpose here? If you just want to examine the item quality, the reliable validity evidence of the items, I think it's okay, it's totally reasonable to do that separately. But if you're trying to calibrate all the items to compare their difficulty, to see which one is more difficult, which one is less difficult, to compare all the items or create a common scale to map all the items with all the persons, then you may want to try a single analysis. So I think that depends on what's your goal, what your goal is. Does that help?
Yeah. Thank you so much, Prof. Thank you so much.
Oh, no problem.
Okay, thank you, Kramo. Okay, Avan, you're next. No
I
song,
cannot hear
no?
you.
Still no song. Avan, still no song. Right, so we have some, can you try again? Oh, okay. So maybe you just type the question, or maybe you come back later, right? So can I give the opportunity to Andy? Okay.
Thank you so much, Professor. Am I audible?
Yeah, I can hear you.
Okay, thank you. Actually, I have 2 questions, Professor. First is, since the beginning, the Rasch model is individual-centered test. It is just pop up in my mind. So is it possible to use this model for just one person, or we have to have a group to test the individual? Also, the second question is, based on your explanation in your presentation, you give us an example for some group that that is what if I remember it, 10 items in 6 person, right, Professor? So, I wondering, in one time test, how many person in one test that should, I mean, ideal one in one test? That's have a correlation with the first question. That
Yes.
is it possible for one person? If it's not So how many a person in ideal range? I mean, think.
Yeah, that's a very good question as well. So one traditional use of Rasch model is to create a norm scale. So for instance, with SAT, what you get your score is actually a percentile, right? So what they do is that they create a norm scale, and then no matter how many people come in, they just compare your raw score with this raw score to latent score conversion table. So in that sense, it's like we create a ruler first. But when we create this ruler, we need a lot of people. We need a lot of sample. And also we may need a pool of items to find the proper anchors. Once we created this ruler, then we can just use that to measure any person. It can be a group, it can be a single person. So I think your question is we need to put that into a context. So we usually view this scale or the kind of the measurement into 4 stages. The first stage is development. The second stage is evaluating. The third stage is maintaining. And the last stage is using. So if we're in the developing, evaluating, and maintaining stage, we may need a lot of people. We may need a large sample. Not that large, but we need more people, definitely not one, to calibrate, to find the problematic issues, and also to see if it can be used across different samples, different populations, or different time points. But when we use this scale, eventually it doesn't matter, because we just use that to actually measure which this person is at. So for instance, the global scale for the food insecurity, I showed as a quick example earlier as a measurement in the social science. So when the United Nations developed that scale, they just use that across the countries for collecting the measures. So in that sense, they already have the scale. So they just need the person measure to match with the standards on the scale. So it doesn't matter how many people involved in this study when they collect the measures. It can be just a single person from a particular country. Once this person completed the survey,
score of this person, then we just map onto the scale. We just compare with a ruler. So I think you got the idea, right? So if you're using the scale, using the ruler, using this measures, it doesn't matter. But when we develop it, when we evaluate this scale, we need more. And then for a second question, there's no kind of the rule of thumb for the sample size, but usually in this field, we see more than 30, not less than 30, but also it depends. So for instance, in this creativity data set, you see that I have 3 facets, right? 2 items and 48 persons by 45 readers. So that generates a lot of data points. So it's not just how many students I have. It also involves a third party, involves the raters. So when I have a lot of raters who give the ratings, the data matrix actually is very large. I have a lot of data points. So that's also a large data set. So the sample size is one hand, but also we need to think about the actual number of data points we have. But if you have only 2 facets, we say 30, maybe, not less than 30.
Okay. Thank you, Prof. Wang. Okay, so I think Andy already got the point, all right? So, Afan, you want to try again?
Yes, Prof.
Oh,
Am
yeah,
I
go
audible
ahead.
now? Okay. Yeah, thank you, Prof. Wang, for the presentation. I look at your slides and particularly on the on your paper on subjective creativity assessment. Yeah, you group the students into 2, gifted and non-gifted classes. So what I understand in this model is the main facets are 3: the reti, the rater, and the task. And yet you create another facet which grouping the ready or students in this case. Can we make a group? For example, I want to do a rater analysis. Can we do groupings on raters based on demographic data? I mean, several demographic data like educational background or teaching experience or so many. The point is how many is the limit for the, because this would create a lot of for example, we have 5 another grouping of raters, or maybe more than 5 groupings of rater. How is the analysis? Is it possible or thank you for the.
Yeah, that's a good question. So we actually had a related so we got a pushback earlier by doing this kind of analysis, by having the individuals and also grouping variables analyzing in a single analysis. We got a pushback once, but what we found is that they had a point statistically. If we have the individuals, right, the reader, students, and items, and also have the grouping for the students, these two facets seem to be related. But usually with the parameters in the manifest Rasch model, we want all the facets, all the parameters to be independent. And that's an assumption. So statistically, also theoretically, I think that makes sense. So one time the reviewer actually suggested us to do 3-stage analysis. The first stage is to analyze students, readers, and tasks, only 3 parameters. In the second stage, let us fix the estimates of those 3 facets and then add in the student group and the reader group. In the third stage, if we want to do the differential item analysis, differential item functioning analysis, then we add interaction term. So we tried it, but the difference is very minimal. So the 2-stage with versus a single analysis, including the grouping variables in there, the estimates eventually are very minimal. It's like the rounding error. The difference is at the second decimal place, very, very minimal. So that's what we wrote back. So we really understand their concern and we agree with it. But when we run it, we found that this program may have something to do with it. It may correct it, or it may have done something to separate the estimation for different parameters. So it doesn't really affect. So adding the demographic variables, it doesn't affect the estimates of the student, readers, and the items, the tasks, measures. And that's kind of gives us some confidence for running this just all at once, since it's easier, right? And then another paper, actually, I had a few more that's based on a collaboration data set, measuring the team, which actually the last reference I mentioned with the summary of the steps. So in that paper, we actually added a few more demographic variables for the persons. So they are all related to the persons, like gender and their title, their rank title at the university, and all of those demographic variables are related to the persons. So it's like we're adding multiple person groups as parameters into the manifest Rasch model, and we tried it as well with this 2-stage process versus a single analysis. It didn't change that much. So I think it doesn't. From my perspective as a lazy person, sometimes I think it doesn't matter. But if you wanted to be really strict, to be really following the kind of the rules, I think you can do 2 separate stage. So run the analysis without the grouping variables first, and then fix all those estimates in the second analysis to estimate the grouping variables, grouping facets.
Thank you, Prof. Wang. I think the answer is clear for Afan. So actually, we can add so many facets as we want, but the question is it really can result and answer the research question or not? So I mean that is very clear. Technically, with facet software, you can add more facet into the analysis, right? So what you call as source code is not so difficult actually. Right. So another one, Lutfi. Okay, go ahead.
Okay, thank you for the opportunity, and then thank you very much, our professor. You have a great presentation, and then it become motivate me to learn more about trust model. And then I have a question: if I want to conduct a research, especially using the trust model analysis, and then sometimes I use, for example, I use the instrument from the previous study, right? And then I don't know whether there is an item bias or not. So maybe in this case, I should use the diff to make sure which is there is an gender bias or demographic something that impact to the item. So if I use the instrument from the previous study and then we don't know whether there is an item bias or not, so should we always use the diff in our analysis, in our research? Because so it's been that in our result, I just questioning how to report it, like, for example, based on the data that we collect, and then should we state that this data based on this instrument that maybe this instrument have the item bias based on the diff value, that the three indicators value that may be fulfilled in this case. So yeah, how we report that, and then should we always use diff in our analysis? Thank you.
Oh, that's another very good question as well. I got all the good questions today. So first of all, when we use a previously created instrument, we should always examine the psychometric quality using the sample we created, right? So both the developers and users have are responsible for examining the quality of the scale. So we will have to present or provide the reliability of those psychometric evidence based on your sample, based on your current sample. So in the research, in the existing research, I do not really see kind of a common practice to provide the fairness evidence. I'm not saying this is correct. It just people are not getting used to that yet. So usually we see people provide the Cronbach alpha, right, as a reliability index. If they use Rasch model to calibrate, they provide reliability separation. And they provide fit indices as the validity evidence, or they do a factor analysis as the validity evidence. But it's really rare to see they do the differential item functioning as for a scale, for an instrument validation, kind of validation stage. But from my perspective, I think that's very necessary, especially for high stake assessments. For instance, if you're examining a national admission test and you're using that for making some inferences, for writing a policy, kind of informing some policy issues, and then it's very necessary to see, especially if you have those demographic variables, you have the student information like their gender groups, their kind of which type of high school they're from, their majors. If you have those demographic variables, I think it's necessary to conduct the differential item functioning analysis to provide the fairness evidence. But in some cases, especially in social sciences, we may just have like an attitudes scale, right? Like a really more like personality scale. It may not vary that much. It may not, like more psychological scales. So there's a difference. Before I get into it, there's a difference between educational assessment and psychological assessment. So for psychological assessments, usually they do not have that many fairness issues compared to the educational assessments. Because for educational assessment, we're measuring cognitive ability more. But for psychological assessment, we're measuring some traits, like our personality, kind of developmental stages. Those traits or those assessments do not often have that many fairness issues. So with those kind of skills being developed, it's maybe it's not that necessary. Maybe it's not that important to examine the diff. Or in other words, we do not really see that many kind of diff analysis in psychological research, right? We usually see that more in the educational measurement field. So I think that depends on the purpose of the study, depends on the context. But if you're working on a high stake educational assessment, I really highly recommend that you provide the fairness evidence.
All right. Thank you, Prof. Wang. So I think Lutfi also you to have to take note that diff is sensitive to volume of data. Okay, so many sources they said it's at least 200 in subgroup of the respondent or test taker that what you call as required to for diff analysis. Prof. Wang, we still have 3 questions in the chat room. So the first one is from Mr. Sahibul Ahyan. Is it any criteria for the number of the raters for MFRM and how many the minimum and maximum raters?
That's a good question. I wouldn't say there's a maximum of the raters because I do a lot of studies on with a focus on raters. So when the raters become my kind of my my interest, I may have a lot of raters in that case. So I wouldn't say what would be the maximum, what would be the upper limit. But for the lower limit, at least you should have 3. Otherwise, you cannot get the variance, right? And there are studies they simply yeah they have just a few raters so that they can have a better consistency among the raters. So if you really ask for a minimum number, I would say 3, at least 3.
Okay, thank you. Of course, we call it multi-rater, so it should be more than 1. All right, so next one from Miss Nabila Nindya. Hello, Prof. I want to ask what are the drawbacks of utilizing the Rasch model that you often face? So it's your personal experience you have.
Yeah, that's a good question. I wouldn't say drawback, but I think it's worth noting that Rasch model has strong requirements or strong assumptions. With the Gottman pattern I showed earlier, with that hypothetical example, you see that we expected all the students follow that pattern. So they cannot make any sleeping or guessing or error. All of the sleeping and guessing are treated as error. So that will contribute to the residual. So Rasch model actually has a strong assumption of the model or strong requirement of the data. So we're looking for the data that can fit the model, can satisfy those requirements. So I would say that's a strong assumption, and not all the data can meet those requirements. And because of that assumption, it's kind of two-sided, right? A lot of test development, those test industry, they use Rasch model for test development because of that strong assumption. So all the items that can fit the model are good items. So if you make use of this strong requirement, it can work for you really nicely. But if this strong assumption or strong requirement becomes a kind of gives you some hard time for moving forward, for developing your scale. For instance, half of your items do not fit the model. Then I may say change a different model, right? So if this strong assumption becomes a problem for you, then you may go for a different model.
Okay, thank you for the answer. I think it's very clear. So I always emphasize this to students that we are measuring something hidden. We are measuring something latent. If we don't have any fairness assessment, so it's like giving a very hard attack to somebody who are not qualified, then suddenly pass the what you call the exam, for example, which is unfair, right? The last one, Prof, from Mr. Budi Naini. Okay. Would you compare between G theory and MFRM in addressing sources of error and variability? So generalizability theory. Yep.
That's a good question. So we usually view CTT and generalizability theory and item response theory as 3 kind of really key measurement theories. With classical test theory, we have only one kind of a chunk of the error variance, right? We only have one chunk of residuals. And with generalizability theory, it can partition the error sources, the errors due to different sources. So one common use of generalizability theory is to partition the residuals into the to quantify the variation due to student responses, due to the rater scoring, due to the items. So that sounds similar as many facet Rasch model that had different facets. And actually in generalizability theory, it also used the term facets to describe like items, persons, and readers. However, one key difference is that the item response theory or the Rasch models give you the latent estimates, give you the location estimates for the individuals. So that's why it's called individual-centered statistics or individual-centered models. And generalizability theory is still group-centered. It focused on the groups. But I like generalizability, the G theory as well. I think it can, the unique contribution is that Kronbach actually, he developed the G theory. He realized that we cannot just treat all the errors as the same. It may due to different sources. So I think that's a great advantage or the great improvement of the measurement theory. And also I think that the G theory has been really underused. It can have a lot of applications, really good applications in the measurement field as well. So I like the G theory as well. But the difference here is that the G theory focuses more on the, as it says in the title, generalizability, how well we can generalize the scores, and it doesn't focus on the measurement of individual persons or doing item analysis. So yeah, I think just two different focuses of these two theories.
Okay, thank you, Prof. Wang. I think that using G theory, they have some limitation, they have some advantage, as well as also so many advantages you have. So you have precise and accuracy as a result. Okay, so when I'm studying G theory, that's what I have. And then when I'm using Rasch, so it's very clear, clear cut, and so many informative information that I can use. Okay, sorry. And then the last one from Muhammad Maulana. In the context of religious education, what is strategy that you suggest for teachers to measure the level of student belief in God, since faith is something sensitive for some people? Right, it's a good question, Maulana.
That's a very difficult question for me. I don't know much about religious education. And actually, I'm a person who's free of religious beliefs. So that's kind of a difficult question for me. So for the substantive part, for the content part, I do not have any suggestion, because it really requires some experts who are in this field to design the actual items, to design the measures. And the psychometricians actually just work with the numbers, right? Provide the kind of the workflow and help you go through the entire process and do the analysis to show which items or which persons may have some potential issue, and then work with the content experts to revise the scale. So I really like this question, but I'm sorry, I cannot really contribute that much.
All right, so thank you very much, Prof. Wang. So you more than nearly 2 hours plus, and then actually what you already explained, some of you. Okay, so it's very informative books written by also Prof. Wang. Okay, so it's talking about so many measurement theories available for you to analyze, and then you can compare between group-centered statistic as well as for individual-centered statistic, right? So we are very fortunate today to have very good experts and really expert measurement. Okay, so thank you very much, Prof. Wang, and please, can we have give applause to Prof. Wang? Okay.
Thank you all.
And okay, so thank you very much, Prof. Wang. So we will have a contact, and hopefully we will meet in August in KL for the Pacific Rim Objective Measurement Society Conference. Okay, with that, and then the next 2 weeks we have Dr. Jali from Rasch Malaysia for another guest lectures about Rasch model in education assessment class. Okay, with that, thank you very much. Very good afternoon, and then wassalamualaikum warahmatullahi wabarakatuh. Okay, I will close this session. Goodbye, everyone.
Bye.
Thank you.
Thank you.
Thank you, Prof.
Thank you, Professor.
Thank you, Professor.
Thank
Thank you,
you.
Professor.
You're
Thank you,
welcome. My
Mr. Bamba.
pleasure. Bye.
Bye.
Bye.